this video, we're gonna implement the full adder using VHDL programming in Quartus. Next, we're gonna use the full adder as a building block or as a component to create a 4-bit parallel adder using structural modeling in VHDL. First, we're gonna start by creating a new project in Quartus. We're gonna go to File, New Project Wizard. Next, and then we need to create a new project folder. So we're gonna go to Browse. I'll choose the desktop as my project destination, and then I'll create a new folder in the desktop. This way, my project will be organized in one single folder. I'll name my project Adder, for example, and then select that folder. So remember, this is only the folder name, but I can always name the project as the same name as my folder. So I'll name the project Adder as well, and then you can just simply click Finish. Now I have successfully created a new project. I need to start by creating new files so I'll be able to write my code. I will go to File, New, and then choose VHDL file. So scroll down until you see VHDL file and then click OK. Now I've allocated space or created a new window or text file for my code. I'll start by adding the 3 lines for the library declaration, which includes library IEEE use work.all, and finally use IEEE.standard logic 1164.all. These 3 lines declare the library files that I need. Next, what I'm gonna do is start by typing the entity part of the code. So I'll say entity. Remember, we're doing the full adder file using behavioral modeling. A good way to start your code is to type a comment. I'll type a comment with my name, for example. So the way to write a comment in VHDL is to use 2 dashes followed by the comment you're interested in adding. So going back to the entity part of the code, entity is a keyword. Next, I need to type a name for my entity. I'll name it full adder as such. So since I'm not gonna use an underscore, I'll capitalize the second letter in my entity name. Remember not to use a space, since spaces are not allowed, dashes are not allowed in the entity name. The entity name must start with a letter. So my entity name so far follows the guidelines or the rules or the restrictions provided by VHDL. So entity full adder is, and then end the same name of the entity, semicolon. And here I'm gonna declare all the ports for my full adder, which include A, the first bit that I need to add, then B, and I also have CN, the carry-in bit. These are all single bits, that's why I listed them together and separated them using a comma. They're all single bits and they're all inputs. So I'll say in for input, and then standard logic, which means single bit. Then I'm gonna put a semicolon, which will separate this list from the next list. Here I'm gonna list the sum bit. So I'll say S, comma, cout. I also have cout as an output. For convenience purposes, I'm gonna put cout first, but it doesn't matter which order you choose. I'll choose cout first, and then S, and then colon. These are outputs, so I'll say out, and then standard logic. I'm done now with the entity part. We'll start with the architecture part, which will declare the relationship between the inputs and the outputs. So I need to give my architecture part a name. I'll name it behave, because this is behavioral modeling. Any name would work, but since this is behavioral modeling, I'll choose behave, for example. And then off, it will describe what? It will describe the full adder. And then is begin, and then end, the same name of the architecture, which is behave. So this is a template for my architecture that describes the full adder. In here, I'm gonna define each of my output. I have two outputs. The first is cout, and then I have cin. So I will say s, which is the sum bit. Remember, this is the assignment operator. So s is assigned a value equals to a XOR b XOR cin, according to the logic diagram of the full adder. And then I need to define my second output, which is cout. Cout is assigned a value equals to cin and a XOR b, or a and b. Remember that each parenthesis you open, you need to close, so be consistent with that to avoid any syntax errors or compilation errors. One last thing I need to do is to save this file as the same name of the entity. So what I'm gonna do is, to avoid any typos or anything, just double click the entity name. Notice that it's mentioned 3 times in the file. Entity, and then when you end it, and then when you describe your architecture for it. So I will press Ctrl C from the keyboard, or you can also go to Edit, Copy, just to copy the entity name, and then we'll go to File, Save As, or Ctrl S from the keyboard, and then paste the entity name here. Click Save. Now you'll see that the file has a name that matches the entity name. I can start continuing with the rest of the files that I need to define, but just to be safe, what I'm gonna do is compile this file first, just to make sure that it is error-free. You will read all the messages here. See, I have one error. Says cin is used but not declared. I remember I used ci, but here I type cin, so I'm gonna use ci just to be consistent. It's good that I got an error here, just to let you know that you don't have to panic. You can always read the error message, and they're usually useful. See here it says cin is used but not declared, and any signal or any port that is part of the file must be declared as a port, right? And here I declared ci but not cin, so I changed it to ci to match what I declared earlier in the port part of the code. I believe that's the last error in the code that I have, but there is one last thing I'm sure I'm gonna get as an error. You don't have to wait until you get this error message. You can always fix it before you see the message, before compilation even. I click yes to save the file, and I will show you the error message that it is very common in VHDL. The compilation is still running, so I'll wait for it until I see the last message. See, it says top level entity design, whatever the project name is undefined. Whenever you see this message, it has an easy fix. You just need to go to the hierarchy tab, choose files. Depending on which version you have, the files tab might appear here. So just go to the files tab to display all the files that you have, and choose any of the files that are available, and right click it, choose set top level entity. So now my top level entity will be named full adder rather than the project name. Or if you want, you can start by naming your project as one of the files name that you're gonna have to begin with. So just right click one of the files, choose set top level entity, and do this only once. I can run the project now, and then you'll notice that there is no error messages at all. You might see some warnings, and that's fine, but as long as you don't have errors, you're good to go. You could, like I mentioned, you could also write all the files first and then compile, but I prefer to avoid this because oftentimes I use one of the files that it is error-free and then use it as a template. And it is also easier to tackle one file at a time, especially if you intend on copying, for example, the library part of the code. So if it has an error, you're going to have errors everywhere in each of your files. Now, if I copy the library part of the code, I'll make sure that at least these 3 lines are correct for the rest of my project files. Now, this will complete the behavioral modeling of the full adder. We'll move on to how to simulate it later on. Now we'll continue with the adder, or implementing the 4-bit parallel adder. So a problem statement, the problem statement could be, or a question that could be given would be design or implement a 4-bit parallel adder using structural modeling in VHDL. So it's just one line that asks you to create a 4-bit parallel adder using VHDL. You'll need to know that you need to create the full adder first and use it as a component in your structural modeling of the parallel adder. So you can add another comment here saying this is full adder using behavioral modeling. Now what I'm gonna do is copy these 3 lines. These are the library declaration, and then create a new file by going to File, New, and then scroll down till you see VHDL file, because we're doing VHDL language, right? So I'll click OK. Just to make sure, always notice the format here, or the type of your project. Make sure it's VHDL. And then I'm gonna start by adding a comment with my name, and then maybe a description of the file. I'll say this is the 4-bit, or let me type it like this. This is 4-bit parallel adder using structural modeling. So the first 3 lines are the library declaration. I just copied them. I don't have to type them from scratch. Then the second part of the code is the entity declaration. This is a 4-bit parallel adder. A useful name or a meaningful name would be 4-bit adder, 4-bit parallel adder, or simply parallel adder. I'll name it 4-bit parallel adder, but it's going to be in one word. So 4, maybe lowercase bit, 4-bit adder. 4-bit adder. Remember to always start with a letter. Common mistake would be to start with a number 4 and then say bit adder or adder, whatever. You can name it adder 4, for example. So these are descriptive names, yet are allowed by the language. So I'm going to go back to my name from earlier. 4-bit adder. So the entity name I chose is 4-bit adder, and then I'll say is, and then end the entity name. You can always copy it to avoid any typos, and then semicolon. And here, remember, the whole purpose of the entity part is to declare the ports, which means anything that's an input or an output must be declared here, and you need to mention how many bits each of your port is. So here we'll have the keyword port, and then we're going to open a bracket, close it, and in between we're going to list our ports. I'm going to start with the input ports. I have A and B, which are both 4 bits, because the question requires me to create a 4-bit adder. So I'll say A, comma B, colon. The way to say 4-bit signal in VHDL is standard logic vector. However, I need to specify whether this is an input or an output port. It's an input, so I say in. Then I need to mention that it is a vector, or it's an array, right? But the keyword in VHDL is vector, standard logic vector. Now I have specified that A and B consist of more than 1 bit, but now I need to mention how many bits they each consist of. So the way to do this in VHDL is to say 3 down 2 in one word, and then 0 in between brackets. So open a bracket, close it, and then type inside 3 down to 0 if you have 4 bits. If you have 5 bits, you're going to say 4 down to 0. If you have 8 bits, you're going to say 7 down to 0, and so on. Now, I have another input, but it is 1 bit. So I need to use a semicolon to separate it because it's part of a different list. The second input would be, or the third input would be Cn. And then I have Cn is an input. You could name it Cn if you want, or Ci. I'll use Ci. It's an input of type 1 bit. So standard logic is good enough. I'm gonna expand this here a bit. It's not allowing me, it's fine. Okay. And then I'm done with all my inputs, so I'll put a semicolon to continue with my outputs. I'm gonna put it in a new line, just so it's more readable. The next signal would be Cout, the output bit, the carry out bit, and it is 1 bit. So I'll say colon or is out. It's an output of type standard logic because it's 1 bit. Then I'm gonna put a semicolon to list my final output, which is the sum bit. The sum bits, they're more than 1 bit, so I'll say S colon out. It's an output signal, or it's an output port, and then standard logic vector, remember, because it consists of more than 1 array. I know VHDL is case insensitive, but just to make it neater, I'm being consistent. So standard logic vector, and then how long is your vector? It's 4 bits, so I'll say 3 down to 0. I'm gonna close the ports brackets, which is here, so I'll add another bracket, one final one here. Remember, the semicolon is at the outside of the last parentheses that you have. So this will conclude my entity part of the code. Try to type it as error-free as possible, or as your best, but you can always finish it and then compile the file. Just make sure that it is for sure error-free with the help of the error messages that you might get. Now we're going to start with the architecture part of the code. So we'll say architecture. Right. See if it changed to blue, that means you typed it correctly. Architecture, and then I need to give it a name. It's a structural modeling of the code, so I'll say struct. Again, this name is optional, or it doesn't have, it's not a keyword, you can choose it on your own, so I chose struct. And then off, I'm describing now the architecture of the 4-bit adder. I'll copy the name since it's long and I want to make sure it's the correct one. So architecture struct of the 4-bit adder is, remember, since this is structural modeling, begin doesn't follow is, because in between I need to mention all the components and signals that I have. then end the name of the structure of the architecture, which is struct. So now this part is all a template for my architecture part. We'll use the keyword component and then end component. And in between, we're going to list all the components that are used as part of the 4-bit parallel adder file. I have only one component, which is the full adder, and I'm using it more than once, but it's sufficient, or you should only mention it once. And I will mention it here. I'll say for full adder. Make sure the name here matches the same name of the file that you have. So full adder, and then space. I will open the full adder file, copy this line of code entirely where it says port until the end. You can right-click copy or Control-C, and then go back to the 4-bit parallel adder file, and then paste whatever port you copied in here after the entity name. So component full adder, and then declare the ports for the full adder, and then end component. This way will make sure that you won't get any errors, and the order of the ports are accurate and they match the order of the ports in the original file. Don't worry about any contradictory in the port's name here. My file itself, the 4-bit adder, has a port already named CN, but this CN is different from the CN of the full adder. So this is not an issue. It's fine if you have it like this, because later on in here you're gonna do the port mapping, so this will help avoid any confusion. Just to avoid losing the file or anything, I'm gonna save it right now and then save it again once I'm done. So I will double click the entity name, right click copy or Control-C, Control-S, or go to file, save as, and then paste the name that you just copied here. Click save. Just make sure that the file is saved and the type of it is VHDL, or sorry, VHD. The language is VHDL. Now what you're gonna do is continue with the signals declaration according to the sketch that you have or the plan that you've made. For the complete plan, there is another video that's named Adder Lecture or something similar that includes the mapping or the design or the sketch that we're depending on to implement this 4-bit adder. So we'll need some signals. You can say signal colon, and then maybe standard logic or standard logic vector depending on the signals. I'm gonna just leave it like that for now, and then as I need a signal, I'll add it to the list. And then here we'll start with the first full adder that we have. So I'll say full adder 0. This is the least significant bit. It will add bits A0 with B0 with the first carry n, this carry n. So we'll say full adder 0 is a full adder, this full adder, and I need to make sure that the order that I use matches this order. So the keyword is port map. Don't forget this keyword is very important, and there's a space in between. So port map, bracket, close it, semicolon. And in between, here I have A, but when I do the port mapping, I want A0. So anything in port map is actually part of the ports, these ports, or a signal. If it's not listed as a port, I need to include it as a signal here. So instead of B, I need B0, the bit number 0 of this vector. Okay, then for the first carry n, we'll use the carry n of the file itself, the carry-in of the parallel adder. We know that, or we learned that the first carry-in of an adder must equal to 0, but we'll assign it a value of 0 when we do the simulation. This way it's more abstract. We can use this 4-bit adder again and use it as a component, instantiate it twice, so we can create an 8-bit adder if we want. That's why it's better to make it as abstract as possible. Not really as abstract as possible, but never hard code any wire. So for Cn, I'm going to leave it as a variable named Cn, and then comma. Finally, I have Cout and S. This Cout is going to be Cout of the first adder. So it's an internal signal. I will name it Cout 0, because this is full adder number 0, so Cout 0. If you want, you can have Cout as a vector, but I prefer to type it this way, but it's up to you again. So Cout is never introduced in the code at all, and it is not an input or an output, but rather it's an internal signal. So I'm going to list it as a signal, CO0, and it is 1 bit, so I'll say standard logic semicolon. Now for the sum bit of the first full adder, this will be my first sum bit at the output. Now I'm done with the first full adder and my 4-bit adder file. I will use this line of code as a template to continue the rest. Here I'll use it 4 times, right? Because it's a 4-bit adder, so I will instantiate the full adder 4 times, but make sure that the name here is unique. So this will be full adder 1, full adder 2, full adder 3. Next, first full adder adds A0 with A1, A0 with B1, B0. The second full adder, which is FA1, will add A1 with B0. I will do the A and B first and then worry about the rest. Here it will be A2 plus B2, B3 plus A3, because this will be FA3. And then the sum bits as well. The first full adder, FA0, will output S0, FA1 will output S1, then FA2 will output S2, then finally we have S3. Now, the only thing that I haven't touched is these two, the carry in and the carry out bits. The first one I did it correctly. I just need to modify the remaining 3. Remember we said another name for the 4-bit adder is the ripple carry adder. So, and remember we in the diagram we have in the other video, Cout of the first adder is always connected as Cn of the next adder. So that means CO0, I will copy it, and it will be my carry-in of FA1. So it's always like a diagonal. CO0 is Cn of full adder 1. And then first full adder will output Cout1. And I don't have Cout1 at all in my code, so I will copy it, right? Control C or right click copy, paste it here. Control V. Now I'm done with full adder 1, it's complete. For full adder 2, its carry in. The carry in of full adder 2 is equal to the carry out of the previous adder, so it will be carry out 1. And it will output carry out 2. And I don't have carry out 2, so I'm going to list it as a signal, carry out 2, because it's an internal signal. Finally, for full adder 3, its carry in is equal to the carry out of the previous adder, so it will be CO2. And the tricky part is that the carry out of the last full adder that you have is no longer CO3, but it is actually the carry out of the file itself, or the full adder itself. So it is going to be CO, the CO, which is an output. It's a port actually, so I don't have to declare it anywhere. I will Control-C, Control-V here, or simply just erase the number because it's Cout. It's the same Cout as the Cout in the port. This completes my parallel adder file. The only thing left is to simulate it, but before simulating it, we're gonna click on the compilation button. So I'll click Start Compilation. It's asking me if I want to save it. Yes, I want to save my changes, and I will wait just to make sure that I don't have any errors in my code. Chances are, if it's taken time, especially if you're not connecting any device at all or anything, chances are it will compile slowly, sorry. Now I have an error. That's good. This way you can fix it together and learn something new. You can make sure you scroll up till you see the first error message. If you want, you can filter out the messages so you'll only see errors by clicking here. Double click on the first line of errors. It says syntax error at 4-bit adder near 0, expecting a bracket. Three down to 0, then I have CN. We'll compile it again. Yes. The issue was that I hit enter here. I moved it to a new line. Not really. Notice the misspelling here of down to. It's supposed to be down to sometimes, and it's changed to blue, which is a good thing. So if it's good that it is some of the code is color coded. So the error message in this case wasn't very helpful because it's kind of misleading, and sometimes that happens and it's okay. But at least it gave me the line of code where I have the error. I was able to review my code based on my understanding and revised it just to make sure that there is no typos at all. I'm gonna run the compilation again and see if I fixed all the errors that are there. If not, we'll go back again to the error message and fix them one by one. Now the compilation was successful according to the message here, and it says there's 0 errors, 12 warnings. Like I mentioned earlier, warnings are fine, so we can resume with the simulation. So for the simulation, we're gonna need to use another software named Model Sim. I have it open already just to save time, so I'll click it here. The first window you'll see is this small one. Just click on Jumpstart. It will help you to create a new project. So we'll click Create a Project. So even in Model Sim you need a new project, you can name it the same name as your Quartus project, which is what I'm gonna do. But it is important that you put it in the same folder as your Quartus project. I saved it in the desktop, in the folder named adder. So I'll use the same folder. This way it will be very easy for me to add the files that I have wrote already. I'll click OK, and then it will prompt me to create new files or add existing ones. I'm gonna add the files that I've wrote. So I'll click add existing files, and then click browse. Choose all the files that you've created. You can select them like that, use Control, Shift, whatever. Just make sure you include all of them, and then click open, and then OK. Close this window once you're done adding all the files. See the question mark under status. It means that the software doesn't know whether the files have errors or not. So the first step we need to do is to compile them. So we'll right click here and then choose compile all, so we can compile all the files. If you want, you can select one of the file, right click, compile selected. You will do this if there is an issue with one of the files and you change it and you want to compile it by itself. So you'll select that file, right click, compile selected. But generally we'll compile all the files, so we'll do that. And then just make sure that there is no errors in the compilation. So under transcript, just make sure everything is in green, and finally it says 0 failed with no errors. Now we know that our code is error-free. At least there's no syntax errors or compilation errors. The next step is to go to the library tab in here. So just click library and then expand the work tab. So click on the plus sign here and then choose the file that you want to simulate. We'll start by simulating the full adder. Just double click the file you want to simulate, give it some time, and then the object window will be opened for you. Select all the objects. I'll select them by pressing or clicking the first signal and then holding shift from the keyboard and then press on the last signal. Another way to do it is using Control A from the keyboard. So Control A from the keyboard or select all, then right click, add wave. Another way to do it from the keyboard is to press Control A, Control W, or select and then right click, add wave. So first step is to add all the signals that you want to look at. So we'll add all of them. The next step is to specify which signals are inputs. If you forget, you can always check in here these signals, the input ones only. Select the first input, hold shift from the keyboard, select the last input that you have. Make sure that no output is getting selected, only the input, right? So you want to add all the signals to the wave, then select all the inputs only, then right click them, click clock. Since these signals are 1 bit only, so we'll use clock and it will work. So click on clock. This window will appear. For the first signal A, we're not going to make any changes. We're going to click OK. For the second signal, signal B, we're going to double the period of the signal. That means P will change twice as slow as A, which is the case for your truth table. The first signal on the right hand side changes very fast, then the second signal on the left hand side changes twice as slow, and then twice as slow, and so on. Click OK, then 400. We have only 3 signals, so the first signal will be the default 100, then 200, then 400. If you have another signal, it will be 800, 1600, 3200, and so on. You only have 3 signals, so we stopped at 400, 100, 200, 400. And that's all. Now we're done with all the settings that we need to do. I'm just gonna do some rearrangement here, so I'll have a good screenshot or a good visual of the window. I think you can even enlarge it if you want, but I'm gonna leave it like that. The next step is to run the simulation. So there is different ways to do it. The first way is to click on the run icon here. Another way is to press F9 from the keyboard, or to go to simulate, run, and then run 100. So I'll use the icon here, or F9. See it here? There is 2 different different signals. I can zoom in to make everything clear by either clicking on the zoom in or pressing I from the keyboard or the plus sign. So I to zoom in, or the plus sign from the keyboard. See, this is the first combination, this is the second combination. I'm gonna zoom out a bit and then press F9 again from the keyboard. So now I have completed 1, 2, 3, 4 different combinations, but my circuit consists of 3 inputs, right? So that means I'll have a total of 8 combinations. 2 to the 3 is 8. So far I have 4. So I'll click run until I see a total of 8 different combinations. So F9 and then F9. You can scroll, enlarge the screen, scroll to the left. You can also always count again, 1, 2, 3, 4, 5, 6, 7, 8. Now I can tell that my test is complete and it covers all the possible combination. If you want, you can use the cursor, move it around to read the values. The easiest one would be this. If A is 0, B is 0, C is 0, the sum is 0, carry out is 0. You can test all of these, or a few of them at least, and compare them with the truth table of the full adder. You'll notice that it is correct. For the screenshot, it is sufficient to just stop here. So for example, I'll do one right now by opening the snipping tool and then click new, select only this part of the screen. So this is a complete screenshot of the timing diagram of my full adder. If I want, I can also take a screenshot of the code, but make sure to always take a screenshot of the simulation first, just to make sure that it is correct, and then just to avoid redoing any screenshots. And then we're gonna screenshot the code of the full adder like such. You can copy it, paste it in a Word document, and so on. Next, I'm gonna simulate the parallel adder, which I named 4-bit adder. Again, you can end the simulation here by going to end simulation. One more thing, if you forget and accidentally clicked clock on the output or did anything wrong, or put the wrong number for the period, you can always restart the simulation by going to simulate, restart, and then click OK. Then you will have to only redo the clocking. I'm just rearranging things since I messed it up earlier. So this will clear all the periods that you apply, or the clocks that you've applied to the signals, but you've added them already and they're still there. So again, if you made a mistake with the running or anything, you can always go to simulate, restart. If you're done, you can go to simulate, end simulation, or you can always go to the library tab, run the next simulation that you have. I will run the simulation for the 4-bit adder by double clicking it. It's asking me if I want to continue since there is already one simulation running. Yes, I want to continue. give it some time, and then you will see all the signals that you have, including the internal signals, Cout0, Cout1, Cout2. Notice that next to A, B, and S, I have an arrow showing here, a plus sign, because A is a vector consisting of 3 bits, so 3 down to 0. The same goes with B and C and S. The next step, remember, is to, after double clicking in the library, the next step is to Control A to select all the signals, and then Control W or right click Add Wave to add them here to this window. We're adding all the signals that we're interested in looking at. Okay. So far we've only used clock to assign values for the input, but today, or in this lab, or for this particular circuit, we're gonna introduce something named force. We'll use it to specify a specific value, put a specific value or assign a specific value for a signal. We can test by adding, this is an adder, right? And it's a 4-bit adder. So I can add the number 8, for example, since 8 is consisting of 4 bits. 8 in binary is 1, 0, 0, 0 from the left. So let's examine how to add 8 to 2, for example. So I'll right-click A, choose force, and then write U. I have 4 U's here. That means the value for A is unknown, and it consists of 4 bits. That's why it's 4 U's. I want to change it to 8 in binary, so I'll type 1, then 3 zeros. Click OK. Now I want to add 8 plus 2, right? So I'll right-click B, my second input, and assign it a value of 2. But remember to put all the bits. I have 4 bits, so I need to type the number 2 in binary using 4 bits, like such. Then click OK. Then for Cn, this is an adder, so for Cn I will use 0. Click OK. Everything else is either an output port or an internal signal, so I'm gonna leave them untouched. I've only changed the inputs, A, B, and Cn. I will click from the, or press from the keyboard F9, or you can also click the run button here. Notice that A is now 8, B is 2, S, which is the sum bit, is equal to 1010, which translates to 10 in decimal. I can right-click this signal S, choose radix, change it to unsigned. This way it will be displayed in decimal. I will do the same for A and B, so I'm going to select them both, right-click radix, unsigned. So 8 plus 2 is equal to 10. I can rearrange it too, so I'll have it right next to it. I will press F9 again, just so it will be displayed here. Then once again, I'm gonna select both A and B, right-click force. Try, for example, now 7 plus 3. 7 plus 3. Remember, when you use force, you'll plug in the numbers in binary depending on how many bits you have. Cn is always 0 for an adder, so I'm gonna leave it untouched, and then I'm gonna press F9 from the keyboard, maybe twice, just so it will be complete here. Then I will read the values to make sure they're accurate. 7 plus 3 is also 10. I will do an additional test and I will stop here. So I'll do right-click force, change A to, for example, 6, and then I will put 2 for B. So 6 plus 2 should be 8. I will click run twice to read the values. You can always zoom in if it's unclear. And taking a screenshot like that with all the testing is sufficient. So this way I don't have to take 3 different screenshots, even though I'm doing 3 different tests. So what I'm doing is changing the values of A and B, click and run, do another change, click run, another change, click run. But make sure that Cn is set to 0 if you're doing the adder. This completes the 4-bit adder and the full adder simulation and coding for VHDL. Thank you for watching. If you have questions, please email me at alatia@auk.edu.kw.